One of the advantages of the real form of the Fourier series is that you can actually draw the partial sums. So if we just sum the real Fourier series from n equals 0 to n equals 6 for the square wave, this is the sort of thing that we get. This is the sum of those terms up to n equals 6. And this is a typical term for a given n. And here's a view of the different sinusoidal terms. Of course, for n equals 0, we have 0, but for n equals 1 through 6, we have these sinusoids. This is just a representation of their amplitudes. But they add up to this. So even only taking those first 6 sinusoidal terms, you're already getting a reasonable approximation of the square wave. Here they are again, the 6 sinusoidal terms, which look like this. And here are the individual sinusoids. So these add up to that decent approximation of a square wave. So what we're going to do in this lecture is to characterize the convergence of the Fourier series to the function that we're trying to approximate. And we're going to do this in a couple of ways that will lead us to look at a couple of theorems due to Dirichlet and Parseval. So to begin with, let's try to characterize the error in our approximation. If we take a partial sum of terms in the Fourier series, let's take the case of the complex Fourier series for now. So let's say we're summing from n equals minus capital N to plus capital N. The term Cn times e to the j 2 pi n over big T times little t. There's the partial sum of our Fourier series. Let's try subtracting that from the function that it's meant to approximate, and we'll call the result the error function for the parameter capital N. So let's try to characterize how big this error signal is. We were just talking about the power in signals, so something we can do is to characterize it by means of its average power. We can find its average power by taking the inner product of En with itself. So let's try doing that. E sub n, E sub n. So if you recall, this just means we take E sub n, multiply it by its complex conjugate, so that just gives the modulus squared of E sub n. Then we integrate it over one period from minus t over 2 to t over 2, and divide by t to get the average. We could write that out. Okay, so this will give us the average power in our error signal. Now, to see what this works out to, we need to substitute in the definition of E sub n. So it's f of t minus this partial sum. Then we have to take its complex conjugate. And integrate with respect to t. Okay. So what do we get when we do this multiplication? Okay, well, first of all, we'll have a term that's just f of t times its complex conjugate. Okay. Then we'll also have a term that looks like f of t times the sum from n equals minus n to n of Cn star times, sorry, these should have been pluses here, but now we're going to get a minus from taking the complex conjugate. Okay, so that'll be the multiplication of the outside terms. Then for the inside terms, we'll have, say, minus f star of t times the original partial sum of c sub n times e to the j 2 pi n over capital T t. And then finally, we will have the product of the two partial sums. Okay, so first of all, this first term will just give us essentially the power in f of t itself. If we multiply f of t by its complex conjugate, we just get its modulus squared. Then what will we get for these sort of cross terms? Well, if we bring the ft inside this finite sum, we see we're multiplying ft by this complex exponential, e to the minus j 2 pi n over capital T times t. And then we're going to integrate from minus 2t over 2 to t over 2 and divide by t. That's really just going to give us the complement of c sub n. And then we'll be multiplying it by c sub n star. So in fact, what we're going to get here is just the sum of the squares of the moduli of the c sub n's. Let's write them as separate integrals now. So the first integral will just give us the average power in f of n. Then this next term will just give us the sum from n equals minus n to n of the modulus of c of n squared. And by the same token, the next term is going to give rise to the same thing. Again, if we bring the f star of t inside here and multiply it by this complex sinusoid, then we're just going to get the nth coefficient in the Fourier series for f star. Okay? But that's just going to be Cn star. So we're in fact just going to get the sum of the moduli squared once again of the c sub n's. And finally, what do we have here in the last term? The two sinusoids just multiply to give us 1. So once again, we're just getting the sum of the squared moduli of the coefficient c sub n. Okay, so we can cancel out, say, the last two of these terms. So we're left with the fact that the average power in our error signal equals the average power in F itself. Don't know what that n's doing there. The average power in the function that we're trying to approximate minus the sum of the squared moduli of the coefficients. And in the previous lecture, we saw that this modulus of Cn squared was precisely the power in the nth term of the Fourier series. And because all of those terms are orthogonal, it turns out that the power in those terms is additive. You can get the power in the entire partial sum simply by adding up the power of each of the terms for each value of n. So the power in the error signal turns out to be the average power of F minus the average power, the sum of the average powers of each of the terms in the partial sum. Now, what does this mean? Okay, this is interesting. We can, in some sense, characterize the power in the error signal, and we can see how the power in that error signal decreases as we add terms to our partial sum. Let's look at the result for the square wave. And we'll write out the average power of the partial sum as a percentage of the average power in f of t. So if capital N is 1, in other words, we just take one single term, one single frequency in terms of a term at the fundamental frequency, then we already get 81% of the power in the square wave. If we go to n equals 3, we get 90%. For n equals 5, we get 93.3%. And for n equals 7, 94%. So in terms of power, we seem to be converging reasonably quickly. But do we actually converge? Does the series actually converge to a square wave? Well, it used to be thought that that was impossible. The square wave is not continuous, not a continuous function. We're just adding up continuous functions. You might think that you couldn't get very good convergence, but it turns out that you do, in fact, get very good convergence, as summarized in the Dirichlet convergence theorem. For any piecewise smooth function, we get very good convergence. So if we have a piecewise smooth function f of t, on the closed interval from minus t over 2 to t over 2, if we sum the entire Fourier series, then for a given value of t, it actually converges to f of t itself. Value of t. And of course, for piecewise smooth functions in a given finite interval, you have only a finite number of discontinuities. So almost everywhere, it converges exactly to f of t. The only remaining question is what happens at discontinuities. So what happens, for instance, at the jumps in the square wave? There, it does something eminently reasonable. It converges to the average value of the limits from the two sides as t approaches the value of the discontinuity. So you can't ask for much more than that. As long as your function is piecewise smooth, the Fourier series converges to it everywhere where the function is continuous, except at that finite number of discontinuities that you may have on this interval for your piecewise smooth function. And where there are discontinuities, where there are jumps, it converges, if you like, to the midpoint of the jump. Okay. So that's the Dirichlet convergence theorem. And if we combine this with our result on the error function, given that the Fourier series converges almost everywhere to f of t, the power in the Fourier series, the total power in the Fourier series, must be the same as the average power in f of t. Okay? So the power in our error function, we know, must converge to 0 as the size of our partial sum increases. So if we take the limit as n goes to infinity of the inner product of our error function with itself, that must equal 0. I should say another way to say this. We have what's called Parseval's theorem, which says that the average power in our piecewise smooth function f of t is simply the sum from n equals minus infinity to infinity of the modulus squared of the Fourier series coefficient c sub n. This, of course, is for piecewise smooth functions. We talked about the real valued sinusoidal form of the Fourier series coefficient, of the Fourier series rather. And in that case, Parseval's theorem says essentially the same thing. It says that the average power in f of t equals, first of all, the average power in, if you like, the DC component. When n equals 0, the cosine term is just the constant a sub 0. So its average power is a sub 0 squared. And then we saw that the average power in a real sinusoid is 1/2 its amplitude squared. So after that we get 1/2 the sum from n equals 1 to infinity of the power in the nth cosine term, that is 1/2 an squared, plus the sum of the average powers in the sine terms. It's easy to see why this is so. Recall that in the original complex form, what we're doing is summing the moduli of the Cn squared. Well, we know that the modulus of C sub n squared is equal to the square of the real part of C sub n plus the imaginary part of C sub n. Okay. The real part of C sub n is just for the sinusoidal terms, 1/2 a sub n squared. So this is going to give us 1/4 a sub n squared. And this will give us 1/4 b sub n squared. And now I've forgotten to take account of c sub minus n. C sub minus n will also give us 1/4 a n squared plus 1/4 b n squared. And we're adding up both the modulus of c sub n squared and the modulus of c sub minus n squared in our original version of Parseval's theorem. So we have to take account of both of them. And that gives us our 1/2 a sub n squared plus 1/2 b sub n squared. And we also have that c sub 0, the modulus of c sub 0 squared is a sub 0 squared, because that's just the c sub 0 and a sub 0 are just the constant terms in the respective forms of the Fourier series. So this explains the form of Parseval's theorem for the real sinusoidal form of the Fourier series. Okay, so again, Dirichlet's convergence theorem tells us that as long as our function f of t is piecewise smooth, then the Fourier series converges to it almost everywhere, except at the discontinuities where it converges to the midpoint of the jump. That means, consequently, that the power in the error signal must go to 0, because the power in the error signal was just the power in f of t minus the power in the partial sum of the Fourier series. But if the partial sum converges to f of t almost everywhere, then that means that the power in the error signal must go to 0, because the error will only be non-zero at the finite number of discontinuities that we have in every period. So if we add up the average power in the error signal, that's just going to give us 0. Therefore, we have Parseval's theorem, which tells us that we can get the power in f of t itself by simply adding up the moduli squared of the Fourier series coefficients. That's for the complex form of the Fourier series. And for the real form, we add up a0 squared plus 1/2 an squared for every n, and 1/2 bn squared for every n. That is the average power in the DC component and the average power in each of the sinusoidal components. We should take a look at what we get in the case of the square wave again. So what's the average power in the square wave? Well, if we take the absolute value squared of the square wave, it's always equal to 1. So the average power in f of t is going to be 1 in that case. The Fourier series looks like the sum from n equals minus infinity to infinity of 1 over j pi n. So this is just for n non-zero. 1 over j pi n times 1 minus minus 1 to the n. These were the Fourier series coefficients for the square wave. So we take their moduli squared and add them up, and that will give us the average power of the square wave itself. Now we can simplify this a little bit because when n is even, this will just give us the term in the square brackets here, will just give us 1 minus 1, or 0. So we're only interested in the odd values of n, and for those odd values, this will give us 1 minus minus 1, which will give us 2. So what this will give is the sum from n equals minus infinity to infinity, where n is odd, of 4 pi squared n squared. Or in other words, 4 over pi squared times the sum for odd values of n of 1 over n squared, sum of a geometric series. So you can see that these terms die off pretty quickly. This is a geometric series, which perhaps explains the rate of convergence we observed when we looked at the pictures of the square wave, the partial sums of the Fourier series. And in fact, we looked at the partial sum of the real valued Fourier series. We looked at the sum of the first n terms and saw that it seemed to be converging pretty quickly. Another thing that this can give you is an algorithm for computing the value of pi, because the right-hand side depends on pi, the left-hand side does not. So in fact, you can solve for pi. And get pi equals 2 root 2 times the sum from n equals 1 to infinity. N is odd. Sorry. I should have rewritten in this last line, I should have written n equals 1 to infinity. N odd. And change this 4 to an 8. Because whether n is positive or negative, you'll get the same value in this series. And with that, you get pi as the square root of 8, or 2 root 2, times the square root of the sum of this geometric series. So a byproduct is that we get an algorithm for computing pi. So that's a quick lecture on the convergence of the Fourier series. Once again, for piecewise smooth functions, you get excellent convergence, just that at discontinuities, the series converges to the midpoint of the jump. And you can see from that you get Parseval's theorem, which says that the average power in the function f of t, the piecewise function f of t, is equal to the sum of the squares of the moduli of the Fourier series coefficients. In future, we'll use Parseval's theorem in solving some little design problems involving Fourier series. But let's end this lecture, and in fact this week's lectures, here at this point. See you next time.